Ah, perfect. Um, where am I on the camera if I stand? Anywhere here? Perfect. Hello, it's me. I'm Wen, and this is joint work with April Gonçalves and with very helpful input also from Connor, from Oleg Renres, and from Paulo Toens as well. I'll be talking about bits and bobs for when you actually build a type checker. So I'm a person who builds things, and in order to help me build things, I built a thing, and I'm here to tell you that you can use it too if you want. I'm also going to tell you about a fun little technique in Haskell and a fun little implementation strategy for thinning composition. There we go. So let's say you're building a type checker and you love Haskell and you love nameless representation. Don't argue with me on this. There isn't the time. So you're doing a fairly standard thing that Connor has delightfully set me up for, which is you build a data type. You want the Brown indices, and so you use an integer to represent the Brown indices. Example terms in the bottom left corner. And it's all working fine, and you're so happy. You love nameless representation. And then you get to actually implementing substitution and evaluation. And oof, it's so difficult to make sure all the plus ones and the minus ones go in the right places. So 10 minutes later, you're crying and you're like, why is the number wrong? I don't know where I forgot to add and or subtract something. So you do the thing that we saw exactly just now on Connor's slide, which is where you use the natural number indexing technique, where we have above, we have the type of x is now reaching in and grabbing something out of n things. And then your term becomes indexed by the number of things in scope as well. Some example programs, again, in the bottom left corner. And now you implement evaluation and substitution, and they're really easy. The type checker, you can make mistakes, but the type checker does helpfully remind you where you have to make adjustments of some sort. And it's very helpful and very nice. And your implementation is done, and it works, and it's correct, and then you run it, and you're like, why is it so slow? I am so sad.
More than 10 minutes later.
Oh, yes, sorry, I didn't factor in the running, yes. Now, do you ever wish you could have it fast and safe? With the power of pattern synonyms, view patterns, and lies, you too can have that. So basically what we can do in Haskell is we can take that integer representation and lie and lie and lie until it's a wonderful, safe, inductive definition. How we do that is we take our x definition that is indexed on the type level. We shout unsafe just to ward off anyone who thinks it's safe and put the integer there. And then we, the stuff in the bottom left, it doesn't type check, but it's just there to give you the idea. You just lie, well, you lie somewhat safely about 0 being 0, plus 1 being plus 1, and minus 1 being minus 1, with the corresponding action on the type level. I have sneakily also defined a thing called P. So now we have Z for 0, P for predecessor, and S for successor. P is defined in the bottom right corner, as you would define it. It is a partial function. And then we also define an eliminator. And the eliminator will just do the standard thing when you eliminate a natural number, or an index in this case. And it will do the exact thing where it says, if it's 0, then do the 0 thing. If it's a successor, do the successor thing. And then you do a second stage of lying, where you now define the base functor type for the safe index. So the base functor type is basically the type that would let you take off one constructor at a time and leave the rest untouched. And you define projections and embeddings from and to the base functor type. So if it's 0, you return the actual ZF base functor for 0. And if it's a successor, you return SF, the base functor for successor. And you do these projections both ways, and you can tell with the function that is named thusly because otherwise it doesn't fit on my slide. We have this function UC, which is a deeply unsafe course, but it doesn't matter. It secretly works out. And then what we can do is we can define pattern synonyms in Haskell to go full circle and define Z and F as a nice inductive set of family of data family that translates to these projections and these embeddings. And when you use them in practice, GHC is smart enough to inline everything and leave you with the pure things that say +1 and -1, almost all of the time. And so now you have safe constructors wrapped around an integer, and you can have the best of both worlds. So we can write a function like this, thinning. In this case, the thinning, that means make space for one extra thing at this place in our scope. And we can define it the normal inductive way. And it'll be faster, sure. It won't be a lot faster because it's still a linear complexity inductive definition. But it will look the same as you would normally write it. But of course, that's not really the point. Thinning is part of our standard API of like working with de Bruijn indices here. So we should make it go fast. And so we just coerce the standard function for thinning that says, if the place where you want to make the new hole appear is before the number, then it needs to go up by 1. But if it's after, then it's all good. And then what we end up with is a nice constant time function that acts exactly the same way and presents as a nice safe operation. Right, sorry, I was talking about thinnings, not just thinning. So thinnings, choosing m things from n things. Nope, choosing n things from m things. Those are the same sounds, basically. You didn't hear that I got it wrong the first time. But choosing n things from m things, we can define it sort of like this. It's not really perfect, but it's fine. So we can be done and keep everything, or we can keep this next thing and then carry on, or we can drop the next thing and carry on. And as Connor mentioned, these things act represented as bit vectors. So I have an example again in the bottom left, where if we have keep, drop, and then we're done, we say we have the list of numbers at the top, and we apply this, then we will end up with a list of numbers at the bottom, with now holes where we've dropped stuff. And we can indeed super easily represent this as a bit vector, where 0 is keeping, 1 is dropping, and then afterwards we just carry on with how many zeros we need to fill out our numeric type. And if we do this, we can use the same technique to thinnings. There we go. This stuff has appeared. So again, what we do is we take this unsafe new type declaration, we wrap a word, and then we define the reflexive keep and drop constructors by bit shifts and masking of various sorts. It doesn't really matter, but it works out this way, and I'm not going to go through all the rest because we know it from the previous definition. Do you want this one? Nope.
Does that limit you to a fixed number of variables?
Sorry?
Well, is it a fixed size bit set?
So I'm using word here. Word is indeed a 64 bits variable. So I will get to that in a second. But yes, if you have a scope that goes more than 64 variables deep and you're using this at the moment, then your program drives off a cliff into undefined behavior or into overflow errors. There are different things you can do, which I'll get to in just 1 second. Anyway, thinning composition, thinnings. We can also thin that. We can now define that inductively like this on the unsafe data type, and it will work just fine. However, I haven't learned my lesson. We need to make it actually fast. So the second thing is we can define thinning composition in terms of more or less 3 assembly instructions. So that is the logical OR, logical negation, and the parallel bit deposit operation, which is an x86 specific operation that does exactly what we need so that we can get the whole thing done in 3 instructions, more or less. I mean, GHC might insert a little D reference here or there. ARM can also do this some places, but your MacBook can't because Apple doesn't support the specific instructions we would need for that. So now we have thinnings into a 3 instruction operation that is quite nice and honestly starts making it reasonable to even encode variables as 1 thinnings, because then this composition is exactly what you would need for thinnings to act on thinnings and variables, and it would all be quite nice and fast. Yeah, okay, cool. Now I said you can use this if you want. No, speed run first. I said you can use this if you want. It is on Hackage if you want to try it. Is it safe? Quick check says so. I have fairly exhaustively tested the unsafe definitions against all the safe definitions, so they act all the same way. I have not proven the safe definitions correct, so I might have made a mistake there. I'll find out once I start using this more intensely. As the question was asked earlier, do I use a word? Yes, it absolutely drives it off a cliff if you have more than 64 bindings. Small TT uses a word to represent thinnings and does fine. Oleg Granus did some tests on the language that he implemented and found that the maximum scope depth encountered there is about 27. However, I have also implemented it on naturals, which means you can go on forever if you want. It'll just get slower eventually. For integers, the same. If you use integers to represent your De Bruijn indices, yes, sure, it'll break once it outruns an int type. But if you have more than 2 to the power of 31-ish nested variable bindings, you probably have a bigger problem than your program behaving in a weird way. So yeah, it is correct. Is it fast? I say yes. There are some graphs here that also say yes. Specifically, you can very clearly see, if I zoom in, that thinning with the thinning operation, for instance, with indexes, the green stuff, that is the very clearly linearly scaling thinning using the safe implementation, whereas the other lines are the constant time versions that are unsafe. And the same for thinning composition. It gets a little bit more wobbly in order to show the linearity, but the wobbles in the bottom, that's constant time. It just deformed by my measuring. And then the other one does very clearly, the safe version does very clearly scale linearly. That's, by the way, that's memory usage on the directions. Memory usage on one side and runtime on the other, so both scale linearly. Perfect.